Hello, today we're going to talk about an important topic called composition of functions, and we're going to start by thinking of some examples. Think about this series of pictures, and you can think of a piece of bread as your input and a toaster as a sort of function. You're going to put the input into the function, and then you get a certain output. Another example is this one. You've got an orange. This is your input. Your function is this juicer. So you're going to put your function or your input into the function, and out of that process comes your output, which is orange juice. But sometimes there are these processes in which there's more than one step, more than one function. And so this is the idea of a composition of functions, where you're going to take multiple functions and compose them together. You're going to do one right after the other. And so an example that we can think about is washing machines and dryers. So your input to a washing machine typically is some dirty clothes, right? So these dirty clothes are going to go into our first function, which is the washing machine. And out of that washing machine, our output is clean clothes, but they're all wet. So wet, clean clothes. We're going to take this output and use it as an input into our next function, which is the dryer. So this same output now becomes an input for another function, the dryer. And then out of the dryer, this new output is clean, dry clothes. So, and we should say that our first input were, it was a stack of dried, dirty clothes. Okay, this is a typical idea of a composition of functions, where you have an input, it goes through a process, you have an output, you take that output and you use it as an input for another process, another function, the dryer, and you'll get an output. Think for a minute if we switch these two functions. What if we put dry, dirty clothes into a dryer first, and then what would our output be? Dry, dirty clothes into a dryer the output would be exactly the same. They'd be dry, dirty clothes. And then say that we put that output into a washing machine, we would come out with wet, clean clothes at this point. So if we were to switch the order of these functions, it definitely would make a difference in the ultimate output. So when we are composing two functions, and we'll get to some examples of equations in a minute, the order definitely matters. What function it goes into first will determine the outcome. Okay, so those were some examples to get us to the idea of a composition of functions. And now we're going to get more specific and more precise about exactly what this is. So by definition, the function, and we'll call this one h of x equals f of g of x. So a lot of letters, a lot of parentheses here, is the composition of the function f with the function g. H is called the composite function. So you probably heard me say it, but when you see this expression, this is read f of g of x. And the idea is we've got this input x, and it's going to go into a function. And the very first function that it hits x is going to first go into the function g. And out of the function g, we'll have an output. And we typically call this g of x. But then that output is going to become the input for another function. We're going to stick that into the function f. So x goes into g, it comes out as g of x, but then we stick that into f, and it comes out. And we have our f of g of x, and this is our ultimate output. Okay, so let's look at some examples. The first example I want to look at is, say that you have f, this function. So this is written a little bit differently. Usually we use f of x, but hopefully you'll see in a minute why I use this notation. But essentially anything inside the parentheses is your input. So the function f says take an input and then take the square root of that input. So for example, f of 9 would be square root of 9, which is 3. F of 16 would be square root of 16, which is 4. Okay, so this is a function that just takes the square root. We have another function we'll call g of x. And this function, this is the rule for this function. Okay, now we're going to find a bunch of things out. Our first job is we're going to write f of g of x. Okay, so we have the two functions here. So f of g of x is going to be, we'll start from the inside. We want to think of putting the function g into the function f. So this is literally equal to f of x plus 5, because this is what g of x is. So it's as if I'm taking this whole expression, and this is my input for the function f. And so that would equal, let's see, the rule for f is take the square root of whatever the input is. And that's it. F of g of x equals the square root of x plus 5. Okay, our next job is we're going to find f of g of 4. So this time we have a specific number that's going to be input through both of these functions. So this is f of, we start on the inside, g of 4. Okay, let's think for a minute. G of 4 means go to the function g and put 4 as an input, so that would be 4 plus 5 is 9. Okay, so g of 4 is 9, and f of 9 is take the input and take the square root of that. So the square root of 9 is 3. So f of g of 4 ultimately equals 3. You put the 4 in the middle, while it's just gone through g, it comes out as a 9, and you put that into the function f, and then it comes out as a 3. Okay, let's find f of g of 11. So this time we start inside again. G of 11 is, go to the function g, that'll be 11 plus 5 is 16. Okay, so g of 11 is 16. So we need to find f of g of 11, but that's 16. And so this is, take 16 as an input to your function f. Square root of 16 is 4. Good. Okay, so in general, oh, by the way, we're going to use, so for every different topic, we've been using different pictures. Baby Yoda, Little Women. We had a saying about today is a good day to be proud of all the progress I've made. And for 7.3, for composition of functions, we're going to be, whenever you see these Russian nesting dolls, you know we're talking about composition of functions. And we're going to use this because these functions are sort of nested into each other. Okay, so in general, if you had something like this, f of g of 2, that you're asked to find, you start in the innermost part. So start here. And then you think, okay, this is my input, 2. And then next, I need to put 2 into the function g. So then here, take 2 and put it into the function g. And then, after I find that, I'm going to put it into the function f. So then put it into the function f. So you're sort of working from the, working from the inside out. Okay, a few more examples here. I think you're probably getting the idea of composition of function. The notation sometimes can be a little bit to learn, and so that's why we're going to go through several examples. Say we have f of g is the square root of g plus 3. That's our first function. And g of x is the function 2 over x plus 1. And the first thing we're asked to do is find f of g of x. So compose these two functions in this order. So we're thinking about taking the function g and putting it into the function f. So f of g of x will equal f of g of x. And g of x is this. So f of 2 over x plus 1. So that means take this whole expression, and this is your input for the function f. Wherever there's a variable in f, we're going to put this whole expression. So that means it should equal, let's see, input, which is 2 over x plus 1 plus 3. And that's it. This is f of g of x. This is the composition of those two functions. Okay, let's find g of f of x. So this time, just like the washing machine example, the order matters. And so if we compose these two functions, putting f into the function g, we'll probably get something that looks a little different. So g of f of x means take the function f and you're going to put it into the function g. So this function is going to go into g. So this will equal g of, let's see, f is the square root of your input plus 3. So square root of our input, and instead of g, I'm going to use x because right here they're asking me to use x as an input. X plus 3. This is the function f of x. So g of that is going to be 2 over my input plus 1, and this is my input. So 2 over my input plus 1. And that's it. This is g of f of x. This is a new function, which is the composition of those two functions. Okay, last thing, I'm going to find f of g of 3. There's different ways I can do this. I'm going to use this formula up here that I just found. I know I have a formula for f of g of 3. So this will be the square root of 2 over my input plus 1 plus 3. And we can simplify that. 2 over 4 plus 3, which is 1/2 plus 3 which we would write as 7 halves. This is 6 halves, so 6 halves plus 1 half is 7 halves. And this is it. So for this function, we're literally taking 3, inputting it into the function g, and when you put it into the function g, out comes 1 half, 2/4 or 1 half, and we take that, and that goes into the function f, so 1 half plus 3, and out came this result, square root of 7 halves. This next example is an important example because we're going to mix up a lot of different ways you can compose functions, because functions can be represented by equations like we've seen, but they can also be represented by tables and even graphs. So we're going to talk about how to compose functions when all you have maybe is a table or all you have is a graph. So we'll use all 3 as we compose functions. So 3 functions I'm going to give you are, we'll say f of x equals x squared minus 1. That's the first one. Nice and straightforward. The next function I'm going to give you is a table, and it's represented by an input t and an output g of t. And this is the table of inputs and outputs. 2, negative 3, 3, 4, and 4, negative 1. And the last function I'm going to give you is a graph of a function. And this is y equals h of x. And all we know about it is that these are the xy values for this function. So for example, when x is 2, y is 1. So that's something that's an input and output of this function. So we have these 3 functions. Let's compose them in different ways and get comfortable with using all 3 ways of describing a function. So the first thing we're going to do is find f of g of 2. Okay, so like we talked about earlier, we want to start on the inside. So we think, okay, our initial input is 2, and we're going to put it into the function g. So let's think for a minute. What is g of 2? Here's g up here. If my input is 2, my output is negative 3. So g of 2 equals negative 3. I'm going to take this, and I'm going to now put it into f. So this is my input for f. So this will equal f of negative 3. And now I look at my function f, and it's described this way. When negative 3 is the input, then this is negative 3 squared minus 1, which is 9 minus 1, which is 8. That's it. So I put 2 into g, I got out negative 3. I took the negative 3 and put it into f, and I got out 8. And this was the ultimate output. Now let's find f of h of 2. Okay, so we want to start by thinking about an input of 2 into the function h. So here's my function h. If my input is 2, that means an x value of 2. Here's 2. And what's my y value? If my x is 2, my y value, it looks like it's 1. So h of 2 is 1. I'm going to take that. This is the output of h, but I'm going to take that and put it into my function f. So this is the input for f. So now I need f of h of 2 is 1. So f of 1 just go up here to my rule for f, and that will be 1 squared minus 1 is 0. And that's my output for the whole composition of this function. Okay, here's a good example. Let's compose a function with itself. Find g of 3. Same process, really. We're going to start here. Find g of 3. So g of 3, go to my function g in my table. My input is 3, so my output, g of 3, is 4. And I'm going to take this output and I'm going to put it right back into the function g. So this is my input back into g. So this will equal g of, let's see, g of 3 was 4. So g of 4 equals, go to my table, if my input is 4, my output is negative 1. G of 3 is negative 1. Let's try to compose A, B, C, D. Let's do h of f of 2. This tells us to start in here, find, when my input is 2, what is my output according to f? So f of 2 is 2 squared minus 1, that's 4 minus 1 is 3. And this is something I'm going to put into the function h. This is my input for the function h. So h of f of 2, but f of 2 is 3. All right, so going to h, let's see. This is my input. This is like my x value. 1, 2, 3. And if my x value is 3, this graph tells me my y value is 0. And that's it. H of f of 2 is 0. Okay, let's compose h with itself. Let's do h of 2. Okay, so again, we start on the inside, h of 2, 1, 2. So h of 2, if my input is 2, this graph tells me my y value, my output, should be 1. And so I'm going to take that output and use it as an input for h. So input for h. So h of 2 is just h of 1. Okay, and if I have an input of 1, so this is my x value for h, the graph tells me my y value is 2. This is it. This is my last output for that composition. All right, let's compose all three. Let's find h of g of f of 2. So you can do this. You can compose as many functions as you want together. But we start on the inside and we work outside. F of 2 is 2 squared minus 1 is 3. Okay, this is going to now go into the function g. So I have h of g of f of 2 was 3. Okay, next I need to work on this one. I can totally do that. G of 3, if my input is 3, my output is 4. So g of 3 is just 4. And lastly, I need to find out what h of 4 is. So my x value is 1, 2, 3, 4. And my y value, the graph tells me when x is 4, the y value is negative 1. And that's it. That's the last output. So I've composed those three functions. Okay, this example comes from Khan Academy. The number of people n that Dennis can invite to his party is dependent on the amount of money x in dollars that he saved up for the party and can be modeled by the function n of x equals x over 25. Okay, so just thinking about this, if he had $50, that would mean he could invite 2 people to his party. If he had $100, he could invite 4 people. If he had $200, he could invite 8 people. All right, so that gives me a kind of feel for that function. The amount of money that Dennis saved for the party, M in dollars, is dependent on the number of overtime hours, H, he worked this week, and can be modeled by the function M of H equals 50H plus 150. So this is the amount of money that he earns dependent on overtime hours. So if he worked 1 overtime hour, he has made $200. If he works 2 overtime hours, he's got $250. So that function gives us the amount of money he's saved for the party. Find a function that models the number of people that Dennis can invite to his party if he worked H overtime hours this week. All right, so that's a lot of words, a lot of stuff to read. Let's see if we can kind of decipher what's going on. Essentially, let's think about this first. X, the number of people N is dependent on the amount of money X that he saved. And that's what we're really interested in. How many people can he invite to his party? Okay, the ultimate question is, we want to be able to go from the number of overtime hours that he worked to the number of people he can invite to his party. So his overtime hours should determine the number of people he can invite. We don't have a direct path there right now, but we've got some, it's like you're hopping over a creek. You've got this, these stepping stones that ultimately will get you across the creek, but you need to step on each stone. So the first kind of stepping stone is, we do know we can go from the number, his overtime hours to the amount of money he's saved for the party. And that is given by M of H equals 50H plus 150. So this will give us an input of overtime hours and an output of money. And then we do have another kind of stepping stone where we have the amount of money he has for the party determines the number of guests. And this is given by the formula N of X equals X over 25. So money is represented by 2 different variables. That's one thing that's just a little bit tricky on this problem. Money here is represented by M, and money here in this formula is represented by X, but that's okay. If we think of things as just inputs and outputs, it becomes a little clearer. Okay, so what we really want to be able to do is go from overtime hours to the number of people. So this is our input. So what if we had something like this? This would be kind of nice because this gives as an input the number of overtime hours, and as the ultimate output, we have the number of people he can invite. Yep, this is definitely what we want to find. So this composition of functions, this is like the rock hopping across the creek. We're first going to let overtime hours help us determine how much money, and then that money will help us determine the number of people he can invite. And what we really want is a formula that just gets us from overtime hours to the number of people he can invite. And we know how to compose these 2 functions, so we'll just go for it. So first we'll think of inputting this into the function N. So this equals N of M of H is 50H plus 150. Okay. So we're going to take this right here and input it into the function N. Here's the function N. So this will look like, this is our input, and this is where the input goes. 50H plus 150 divided by 25. That's it. This is N of M of H. The only other thing I'm going to do is I'm going to clean this up a little because I notice everything is divisible by 25. So if I think of this as 50H over 25 plus 150 over 25, then that equals 50 over 25 is 2h, and 150 over 25 is 6. So ultimately, n of m of h equals 2h plus 6. If he worked 0 overtime hours, he can invite 6 people to his party. He must have some already saved. But then for every 1 hour of overtime, he gets to invite 2 more people to his party. All right, good example. One of the last things we need to talk about is sometimes you're asked to decompose a composite function. So that you're given a function and you're asked to break it apart into 2 different pieces to sort of create 2 functions out of one. And before we look at this next example, I'll tell you, for 2 extra credit exam points, if you'll message me something that you're grateful for today, or something good that happened to you today, then we'll get you those extra credit points. Okay, for our first example, we have a function h of x equals 1 over x minus 2 to the 6th. And we're asked to write h as the composition of 2 functions. These types of examples, there usually are multiple right answers, but we'll go over some possibilities here. So when I see this function, I see 1 over something raised to the 6th power. And so I can think of maybe this part inside the parentheses could be one function. So maybe I could have f of x equal x minus 2. And then if I just think of that as a block, then I have 1 over something raised to the 6th power. I could think of g of x as 1 over something raised to the 6th power. And then I can compose these 2 functions. So I just have to be careful what the order is. H of x would be, it's like you're putting f into the function g. So this is your input for this function. So h of x would be, f going into g looks like this. So f is x minus 2. I'm just going to kind of double check. That would be x minus 2 going into 1 over x to the 6th. Yep, this is the right. So this would be a way to compose, to write h of x as the composition of 2 functions. Let's just do one more quick example. Say that we had, so write h of x equals the square root of x minus 3 raised to the 4th power as the composition of 2 functions. Again, there's going to, with these, there will probably be multiple right answers, but just looking at this, I see something inside the parentheses raised to the 4th power. I'm going to take this whole thing as a function, and this time I'll kind of, just so we get more comfortable with the notation, I'll say I'm going to call g of x, no, not all that, the square root of x minus 3, and I'll call f of x, well, some input is raised to the 4th power, so an input raised to the 4th power. Then h of x would be, it's like you're taking g into f. So g of x is going into f. And that would be one way to decompose those 2 functions. I wanted to give a little bit of initial guidance on number 11 on your homework. You're going to have some tables that translate Fahrenheit to Celsius and Celsius to Fahrenheit. And one of the first things you're asked to do is find C of f of 5. And it's a little bit confusing because you're like, well, both of these tables have, C's and F's. Which table do I use? So you really want to think, of course, starting on the inside, f of 5. This means my input is 5, and I'm going to get an output of Fahrenheit degrees. So this input must be Celsius degrees, and the output is Fahrenheit. So an input of Celsius, output of Fahrenheit, you'll know which table to use. I wanted to give a little bit of a hint on this number 13. You're going to be talking about currency exchanges, and you'll read the whole problem. ultimately you're asked to convert Mexican pesos to Canadian dollars. So Mexican pesos to Canadian dollars. This is essentially, this is your input and this is your output. So really you're looking for something like this, C of M, an input of Mexican pesos and output of Canadian dollars. And you're given input of Canadian dollars to American dollars, input of Mexican pesos to American dollars. So you will have to use a sort of composition of functions, but added to that, you're going to have to, and this is the big hint, you're going to have to take this function and find the inverse of this function. From this function, can you find C of A? And I think you can. Just think of, try some examples out. If you want to go from, this formula gives you going from Canadian dollars to American dollars, but using this you can find a formula for going from American dollars to Canadian dollars. If you have more questions though, definitely come to office hours on Tuesday night on Zoom at 8 o'clock.